physicsinfo.co.uk. Another in the series of Physics GCSE tutorials. Separate science. Topic 7. Astronomy. A very early reminder of the difference between mass and weight. Mass is an absolute quantity that is the same everywhere in the universe. Weight is mass multiplied by the acceleration due to gravity, or the gravitational field strength. So a mass of 120 kilograms would weigh 120 times 10 newtons on Earth. Meanwhile, on the Moon, it would weigh much less because the gravitational field strength on the Moon is about 1.7 newtons per kilogram.
The solar system came into being about 4.5 billion years ago when a cloud of interstellar gas and dust collapsed, resulting in a solar nebula, a swirling disk of material that collided to form the solar system. The solar system is located in the Milky Way's Orion star cluster. Only 15% of stars in the galaxy host planetary systems, and one of those stars is our own Sun. Revolving around the Sun are 8 planets. The planets are divided into 2 categories based on their composition: terrestrial and Jovian. Terrestrial planets, including Mercury, Venus, Earth, and Mars, are primarily made of rocky material. Their surfaces are solid, they don't have ring systems, they have very few or no moons, and they are relatively small. The smallest and closest to the Sun is Mercury, which has the shortest orbit in the solar system at about 3 Earth months. Venus is the hottest planet, with temperatures of up to 867 degrees Fahrenheit due to an atmosphere of carbon dioxide and extensive lava flows. Next to this world of fire is a world of water, Earth. The water systems on this planet help create the only known environment in the universe capable of sustaining life. The last of the terrestrial planets, Mars, might have also supported life about 3.7 billion years ago, when the planet had a watery surface and moist atmosphere. Beyond the 4 terrestrial planets of the inner solar system lie the Jovian planets of the outer solar system. The Jovian planets include gas giants Jupiter and Saturn and ice giants Uranus and Neptune. The gas giants are predominantly made of helium and hydrogen, and the ice giants also contain rock, ice, and a liquid mixture of water, methane, and ammonia. All 4 Jovian planets have multiple moons, sport ring systems, have no solid surface, and are immense. The largest Jovian is also the largest planet in the solar system, Jupiter. Nearby is Saturn, the solar system's second largest planet. Its signature rings are wide enough to fit between Earth and the Moon, but are barely a kilometer thick. Past Saturn are the ice giants Uranus and Neptune. The slightly bigger of these ice giants, Uranus, is famous for rotating on its side. Next to Uranus is Neptune, the outermost planet in the solar system and also one of the coldest. Orbiting the terrestrial planets is the asteroid belt, a flat disk of rocky objects full of remnants from the solar system's formation.
With one astronomical unit being the distance from our Earth to the Sun, you can see that the 4 terrestrial planets are quite close together. The Jovian planets are much further apart, and there's a huge distance between the Sun and the dwarf planet Pluto at the edge of the solar system. Asteroids and comets. Asteroids are lumps of mostly rock, but some metal, that usually originate from the asteroid belt, which is a ring of rocks going around the outside of the terrestrial planets. Comets are large lumps of ice, gas, and dust. They come from the very edge or even outside of the solar system and hurtle towards the Sun, where they orbit and are then thrown back out into space. Comets follow an elliptical orbit. The famous Halley's Comet returns about every 75 years. Various models of the Sun and the Earth and the Moon have existed over time. The geocentric model places the Earth at the centre of everything, whereas the heliocentric model places the Sun at the centre. As long ago as Copernicus, scientists thought the Sun was at the centre, but it was probably Galileo who looked at the moons of Jupiter who finally showed that not everything goes around the Earth. And whilst we're at it, moons go around planets and planets go around the Sun. Put it another way, moons and artificial satellites follow circular orbits around planets. Planets orbit the Sun. Asteroids are lumps of rock originating from the asteroid belt, and comets are made up of ice and dust. They come from outside the solar system and they follow elliptical orbits around the Sun. And using the same principle of centripetal force, the result of a changing velocity of the planets or the moons or satellites, you can see that there is a force towards the centre and a reactive force. The faster a planet travels, the greater the reactive force. So planets that are really close to the Sun have to travel really quite quickly in order not to crash into it. The nearer a planet is to the Sun, or a satellite is to Earth, the faster it travels. On this animation, Mercury is at the top, the closest planet. And you can see quite clearly that Mercury travels many, many times faster than Neptune. This is a visualization of the thousands of satellites orbiting the Earth. You'll notice that the vast majority are very close to the Earth and are therefore travelling very quickly. These nearer, faster satellites are passing over the poles. They are in polar orbit. The Earth rotates underneath them, so they see a different strip every hour and a half or 2 hours. Polar orbits are used for mapping, looking at vegetation, studying the oceans, and of course for spying. Looking at this outer ring of satellites, they follow a much larger, wider orbit. They're travelling much slower. In fact, they go around the Earth once every 24 hours. These satellites stay in the same position relative to the Earth's surface. They are called geosynchronous satellites. Geosynchronous satellites are used for GPS navigation and for communication. To recap, there are two types of orbit: low, fast polar orbits and much higher, slower geosynchronous orbits. Going around in a circle, satellites are constantly changing their direction. Therefore, their velocity is constantly changing. The greater the rate of change in velocity, the greater the acceleration. And F equals ma, so the greater the centripetal force. The nearer the satellite is to the Earth's surface, the faster it will have to travel in order to stay in orbit.
To the ancients, it was a god. To us, it is the powerhouse at the heart of the solar system, a blazing colossus generating heat and light and life, the sun.
Way out there in space, there's huge clouds of dust and gas. And if one of those clouds of dust and gas is massive enough, its own gravity causes it to start to collapse. So it falls in on itself, and towards the centre of that cloud, it gets denser and denser, it gets hotter and hotter. And eventually, the particles that the gas and the dust are made of are brought so close together that they start to stick together. They start to fuse. That's the energy source of a star. The star switches on and begins to shine.
Inside every newborn star, hydrogen atoms are fused together to make helium. This process is called fusion. and it creates the energy that powers every star. What happens to a star during the rest of its life depends on how massive it is at its birth.
A star like the Sun is in a delicate balance between gravity, which wants to make the star collapse in on itself, and the pressure that pushes outwards that comes from the energy that's been produced in these fusion reactions happening at its core. However, at some point in the future, the hydrogen runs out, and at that point, the core of the star will start to collapse in on itself under its own weight. It gets denser, it gets hotter, until a point where you can actually start to use the helium atoms themselves as the fuel for the fusion, pushing helium atoms together and making carbon and oxygen the next heavier elements in the periodic table.
As the star begins to fuse helium, it creates more energy, and that causes the outer layers of the star to expand. One day, our Sun will grow so large it will swallow up the inner planets of the solar system, out as far as the Earth. It will become a red giant. For the Sun, this will be the beginning of the end.
What happens is, as the outer layers of the star get farther and farther from the middle, the force of gravity that they feel is getting weaker and weaker. And actually, the star loses hold of its outer atmosphere. Its outer atmosphere drifts off out into space. It expands out to become a planetary nebula. And they're some of the most beautiful objects in the universe.
Once the outer layers have drifted away, all that is left of the star is its core.
A white dwarf star is the dead remnant core of a star like the Sun at the end of its life. What's left behind is something that might weigh as much as half the mass of the Sun, but it's only about the size of the Earth. So it's an incredibly dense object. It's dead. There's no nuclear fusion going on it anymore. It's incredibly hot, but then over millions of years it will gradually cool down to become a black dwarf.
Some stars, however, are much more massive than the Sun, and they lead very different lives. They are able to fuse heavier and heavier elements inside their core. The star gets bigger and bigger. Some grow up to 1,000 times the size of our Sun, until it has fused elements all the way up to iron.
And once we've formed an iron core, there's no more energy can be got from fusion. That core collapses. The rest of the star starts to collapse in after it, but then it bounces off. There's a huge shock wave, and in just a second, bang, the outer parts of the star are blasted off into space in a huge supernova explosion. These supernova explosions are so powerful that when one of these stars explodes, it can actually outshine the whole galaxy of which it's part, a galaxy of maybe 100,000 million stars.
For these supergiant stars, all that is left is the super-dense core, known as a neutron star, an object that can have a mass greater than our Sun but be less than 20 kilometers across. But for the most massive stars of all, we think when the core collapses, the gravity is so strong, it becomes a black hole, from which not even light can escape.
So stars are actually the places in the universe where the elements are created.
All stars are formed in the dust of a stellar nebula. Our star, the Sun, is a medium-sized star. It will live for about 10 billion years, and finally it will run out of fuel, become a red giant, and then fade away as a white dwarf. Blue stars, bigger than our Sun, will last for a much shorter period of time. They become red supergiants which pulse in and out until they explode as a supernova. The remaining mass is concentrated in the core and becomes a neutron star, unless the star is really massive, in which case it collapses down to become a black hole, so massive that not even light can escape.
The Doppler effect is the apparent change in wavelength of a wave depending on the motion of the source toward or away from an observer. Astronomers observe this effect with wavelengths of light, but we experience it with sound as well.
If you've ever stood there on a street corner and you've heard an ambulance go by, the first thing you hear is a very high-pitched noise, as it's, say, coming from your left and passing by you. And as it passes by you, what you hear are lower frequencies, a very low-pitched sound. So what is happening in that instance is, as the ambulance is coming toward you, the sound waves that are getting transmitted by the horn on the ambulance, the sound waves are compressed. As it goes away from you, those sound fronts, if you could say, get stretched out. So it corresponds to a longer wavelength and a lower pitch. So you hear a lower sound.
First, we'll ride with the trumpet to see how it sounds. Now, we'll listen to the trumpet as it drives by.
A similar effect can be observed with light. The waves coming towards you are compressed, they're a higher frequency. The waves going away are a longer wavelength, a lower frequency. The light is shifted towards the red end of the spectrum.
Is made up of the full spectrum of wavelengths. But the presence of elements such as hydrogen and helium results in black lines in the spectrum. These are the spectral lines for hydrogen, and the black lines appear at the particular wavelengths that are absorbed by hydrogen. Here are the spectral lines for the Sun. By analysing these lines, scientists can tell what elements make up the Sun. Scientists can also use spectral lines to work out whether a galaxy, like this, is moving towards the Earth or away from the Earth. Let's compare two sets of spectral lines for this galaxy as we expect them to appear. The positions of the spectral lines are based on the absorption lines for various elements as they have been measured in laboratories on Earth. If the galaxy was moving towards an observer on the Earth, the spectral lines would shift to the blue end of the spectrum. This is known as a blue shift. If the galaxy was moving away from an observer on the Earth, the spectral lines would shift to the red end of the spectrum. This is known as a red shift. The further the spectral lines are shifted, the faster the galaxy is moving away from the observer, and the further away the galaxy is from the Earth. Astronomers such as Edwin Hubble measured the spectral lines of hundreds of galaxies in the visible universe and found that most galaxies display a redshift. This led to the conclusion that the galaxies were moving away from the Earth and that the universe must be expanding.
Because you only see redshift in objects travelling away from you, when scientists observed distant galaxies and found that they were also redshifted, it proved that the space between everything in the universe was expanding. If you imagine that this balloon is the actual fabric of space, and each one of these dots is a different galaxy, as it expands, the dots get further apart. If they're getting further apart over time, it must mean that at some time in history, all of these dots were closer together. And at this point, when it was all really close together, is what we see as the beginning of our universe. Most scientists believe that the whole universe began in an explosion about 14 billion years ago. This is known as the Big Bang Theory and states that originally all the matter in the universe was concentrated in a single point. So we can see the effects of the Big Bang, but we can also hear them. Scientists have discovered microwaves and radio waves coming from every direction in space. This is called cosmic microwave background radiation, or CMBR. CMBR comes from light created at the beginning of the universe, which, as the universe has expanded, has been stretched into microwaves and radio waves. 1% of the static I'm picking up is radio waves, which are part of the CMBR. So even though it's the part of the radio that you never want to listen to, the part that you're least interested in, it's still really amazing to think that actually that's the sound of the beginning of the universe almost 14 billion years ago. It's impossible to deny the huge impact of redshift on our understanding of where everything in the universe came from.
The Big Bang Theory suggests that the universe was once hotter than the surface of the sun. Well, if there's one thing we know about the surface of the sun, it's that it emits light. What Big Bang Theory is claiming is that the entire universe was once that bright. If so, where is all that light? Well, it turns out that it's right here, pervading the universe. But because the universe was expanding, the light got stretched to longer and longer and longer wavelengths. And although it was emitted, rather coincidentally, as visible light, it got stretched from visible yellow light to infrared to microwaves, radio waves. And those radio waves pervading the universe can be detected with a microwave antenna. Heck, they can be detected with a TV antenna. An old-style on-the-air TV, a few percent of the noise that you get when you tune to an empty channel was from the early universe. Those radio waves are what we call the cosmic microwave background. So the background of microwaves that pervades the universe, because they were emitted during the early expansion of the universe and have been traveling and getting stretched out ever since.
We've shown that redshift is evidence of the universe expanding, but that can support the steady state or the Big Bang theory. Cosmic microwave background, on the other hand, is radiation left over from a single event, the Big Bang, and that's the proof. Redshift and CMB together are proof of the Big Bang theory.
For most of history, much of the sky was hidden, for there are many kinds of light our eyes can't see. And despite the use of powerful technologies that made this light visible, the sky remained veiled because our atmosphere blocked much of the light from reaching the ground. But there was a plan. 4 special telescopes that could fly above the atmosphere and into space, where they could see the universe more clearly, each one gifted with special abilities to see part of the hidden light. Joining forces, they would reveal a more complete picture of the universe around us.
Radio waves pass through the Earth's atmosphere. That's why we have such big radio receivers on the surface of the Earth. Most other EM radiation is absorbed. Telescopes above the Earth's atmosphere avoid clouds and pollution and even the atmosphere itself, and they pick up the full spectrum of radiation. These telescopes aren't nearer the distant stars, they just produce much more impressive images. 30 years ago, the Hubble telescope started to transform the way we see our universe. And that's it. Thank you for watching.